Hello, and welcome to Systems with Matrices. My name is Tuesday Johnson. Here's an introduction to concept. What are matrices? The singular for this term is matrix, and it's not that matrix. We're not talking about Neo here. A matrix is a rectangular array of numbers, just numbers. The augmented matrix of a system of linear equations is the matrix whose rows are the coefficient rows of the equations. For example, if we take this system 2x plus y equals 1 and negative x plus y equals 4, we can, as long as everything's ordered up, right? We have all of our x's lined up, all of our y's lined up, the equal signs are lined up, the constants are lined up. We can take just the numbers from this equation and turn it into a row. There are two x's, 1 y equals 1. Negative 1 in front of the x, 1 in front of the y equals 4, right? Mathematicians, we're too lazy to write ones. They're assumed, right? It's silly of us to assume things, but yeah, here we are. There are many things that you could do with the matrix. It's its own mathematical object. There are like several courses in the study of matrices themselves. We're not going to get all down with that. For this video, we're just going to be discussing how to interpret matrices. So if you learn to use matrices on your own, at least you'll be ahead on the interpretations. So rather than using the methods of elimination or substitution, online or handheld matrix calculators use a Gauss-Jordan process to do the work for you. This result is often said to be in reduced row echelon form, or RREF command on the calculator. And for this demonstration, I'm going to use standard TI-84. It's probably an 84 plus. It looks like maybe the silver edition. So we have our system, 2x plus y equals 1, negative x plus y equals 4, and we can write it in matrix form, write the system in matrix form. We can then use our graphing calculator to enter the matrix, and then we can command the calculator. We can use the commands on the calculator to do RREF, reduced row echelon form of the matrix A, and we end up with 1, 0, negative 1, 0, 1, 3. But remember, just as we could go from system to matrix, we could go from the matrix back to the system. Our first column was all about the x's, so 1x and no y's equals negative 1, x equals 1. 0 x's, so 1y is equal to 3. 1y is equal to 3. And we have our answer, negative 1 comma 3 for this solution. All right? So matrices can do all of this for you. Now, let's solve this system using a matrix. X minus 2y equals 7, 3x plus y equals 0. I'm going to start by writing the matrix by hand. And then I'm going to use this website that I totally encourage you to use as well. And I'm going to let it do the math for me. So the little pop-up comes in, and I enter my matrix, 1, negative 2, 7, 3, 1, 0. I don't need comma, I don't need any of this except for the solve button right here. When I press solve, it'll give me the solution set. It tells me my first variable is 1, my second x variable is negative 3. Notice it doesn't use x and y, but think about how you have your system, right? x1 is in line with x, y is in line with x2. This allows you to get much, much larger matrices and larger solution sets as well. All right, so we find our solution is 1 comma negative 3. I mean, you could test it, find it. This is a great way to solve systems as well. All right, so those two were results of consistent independent systems on the matrices. They just give you an answer. If we have no solution, we might use our RREF command on the graphing calculator, and we'll end up with a nonsense equation in the bottom. 0 x's, 0 y equals 1. How can nothing equal 1? On the online, on the website that I gave you, it'll tell us the system is inconsistent. All right, so there's no solution. If you use the RREF command on the calculator, you'll get a fine system. It's true, right? 0 equals 0 all the time, so that's cool. Nothing ridiculous. But on the website, it even shows you how to name the variables, right? X is equal to 1 minus y, because we know our x1 is x and x2 is y, based on the variables that we use. All right, so we can interpret matrices We could use matrices to help us solve these. We have substitution, elimination, algebraic. That one where we set the solve both for y. Algebraic intersection. And graphing, right? We have all these different ways to solve, but now we have another tool in our pocket that we can use. I really appreciate you watching this one. Don't forget to catch the applications next, because I'm going to do some more word problems with systems. Thanks for watching.